Okay, I've got an aerostandard Otto cycle at a compression ratio of 8. I know the temperature and pressure at the beginning of the compression, 520 Rankine, 14.2 psi. I know the mass of the air, and I know the heat addition. And I want to figure out the thermal efficiency. So, as with most things, I need to go through and I need to figure out the states first. And the states, of course, for the Otto cycle are to find my U values. Okay, so I can look up U1 because that'll give me T1. Okay, now going from state 1 to state 2, that is the isentropic compression. So I'm going to use the relative volume to go from state 1 to state 2. Okay, knowing the compression ratio, knowing my volume ratio, knowing it's isentropic, I can use the relative volume. So I'm going to look up VR1 and then use that to set VR2. Once I have VR2, then I can look up U2. Okay? Going from 2 to 3, that is the heat addition. Right? So if I know the heat addition, know the mass, know U2, I can use that heat addition to look up U3. 3 to 4 is the power stroke. That's an isentropic expansion, so I'm going to use the same idea where I use my relative volumes going from 3 to 4, because again, the compression ratio is just the reciprocal of what it was over here. So that'll give me VR4, and then from VR4, I can look up U4, and then I've set my states, and I can find my thermal efficiency. So let's go ahead and step through all this. So again, U1, okay, I go to 520 degrees for air, which is right here. I can find that my U1 is 88.62, and my VR is 158.58. Okay, so U1 is 88.62, and VR1 is 158.58. Okay, then I'm going to use the idea that my compression ratio R, by definition, is V1 over V2, which for the isentropic process 1 to 2 is equivalent to VR1 over VR2, right? So knowing that the compression ratio is 8, okay, knowing VR1 is 158.8, I can calculate VR2, and I find VR2 equals 19.823. Okay. Now that I have that, I can set state 2 by going back into the table, going to VR2 of 19.83, scrolling down, 19. It's somewhere in between 1160 and 1200. When I do my interpolation, I actually get a U value of 203.58. Okay, so that sets state 2. Okay, now that I have state 2, knowing that my heat addition is 0.9, right, I can say, okay, Q2 to 3 equals my mass times U3 minus U2. Now again, this is 0.9. Given in the problem statement, the mass is 0.0015. Again, I have U2 that I can plug in. From this, I can do the calculation and actually calculate that U3 equals 803.58. 0.58. So now I have U3. And again, 3 to 4 is isentropic. So I'm going to go look up VR3, use my compression ratio to find VR4, and then from VR4 look up U4. So the first thing is I got to find my relative volume at state 3. So I scroll down my U values till I get to 803, which is way up here between 3950 and 4000, which gives me a VR of VR3. Narrative 0.46955 when I do the interpolation, knowing that 803 is my U value. So that VR3 V3 value is again 0.46955. Okay, then knowing that again my R is V4 over V3 by definition of my compression ratio, therefore VR4 over VR3. So I can then calculate VR4 to be 3.7564. Now that I have that relative volume, I can go look up the U value. So I go down my VR till I get, 3.7564, which is right in here between 2050 and 2100. That makes my U value, nope, that's my H. My U value 385.26 when I do my interpolation. Okay, so 385.26. Now you see I have all of my U values. So once I have my U value, my state is set. I can go ahead and calculate my efficiency. And again, my efficiency is going to be those U values. So let me do it this way. That'll be U3 to 4. So that is U3 minus U4. That's my power stroke. My compression is U2 minus U1, and then my Q in is U3 minus U2. Okay, plugging in all of those U values, I can then calculate my efficiency equal to 50.6%. So again, as per usual, find your U values, many of which are done using the compression ratio and the isentropic idea of the relative volumes to set those states. Once I get my states, I can easily find my thermal efficiency from that.